Okay, so in this video we're going to talk about the hyperfine interactions in EPR spectroscopy. So if you have watched our previous video, you know how the EPR works and how we get a absorption signal, right? So let's take an example, right? Let's take copper. Let's take copper 2 plus, right? So copper 2 plus, here we have the copper 2 plus nuclei, and let's assume it has a 1 unpaired electron, right? Let's assume it has one unpaired electron. So here we have our unpaired electron. So now in basics, what we're trying to do here is we are going to apply a magnetic field which will create a split between two states, right? And then we are going to apply a radiation which will cause to flip back into other state. So we are recording the absorption. This is what we're trying to do. Now you know these nucleus over here, they are also having magnetic properties, right? They are also having magnetic properties. So definitely this magnetic signal will interfere with this nucleus, not with just this nuclei. Let's assume this copper 2 plus ion is connecting with another cobalt 2 plus ion. Then our electron signal will interfere by this cobalt 2 plus nucleus too. Our signal will interfere by all the nucleus surrounding, not the ones so far away, just surroundings, right? So these are called hyperfine interactions. We have an equation to calculate how these interactions affect our signal. So you know, if we have an unpaired electron, then we must have an absorption peak like this. This is theoretically, right? But practically this won't be happen. Instead of one peak, we are going to have several peaks. Why we are having several peaks? Because there are interaction, there are interference from other nuclei. So we can calculate exactly how much peaks we would expect by these interferences. We have that equation 2ni plus 1. This is the number of peaks we would expect. Number of peaks we would expect, right? So here this I is based on the nuclei, right? It is a nuclei properties and its magnetic properties. This n is the number of nuclei. So let's take an example to have a clear idea about this equation. So let's assume we have copper 2 plus ion, sorry, cobalt 2 plus ion. So it has an unpaired electron. So we are going to calculate how many peaks we would expect from this cobalt 2 plus nuclei interference with our unpaired electron. So we were given the cobalt 2 plus I value, which is equals to 7/2. Now here we can use our equation 2ni plus 1, which is equals to number of peaks, right? So here n means the number of nuclei which are interference happening. So here we have only one cobalt 2 plus nuclei, so n equals to 1, and I we have the value 7/2 plus 1. Here 2 is 2 cancelling, and 7 plus 1 is 8. So instead of one peak, we would have 7 peaks for our spectrum. So let's take another little complicated example, right? Let's assume we are trying to find an unpaired electron in cobalt 2 plus cobalt 2 plus complex, right? It has an unpaired electron, so we are trying to find the absorption. So this cobalt 2 plus is connected with nitrogen atom, right, is connected with nitrogen atom which has I value of 1, and it is again connected with one OH minus ion which is I value is 1 over 2, right? So we are asked to find out exactly how many peaks we would expect from this interference. So copper's I value is 3 over 2. Okay, let's find out. So here we have to use the 2ni plus 1 rule. This is the number of peaks. Now this you have to be very careful of, right? We have different kinds of nuclei, right? So we cannot use n equals 3 over here just because we have 3 nuclei to interference, because each nucleus are different, so we need to take them separately. So let's take them separately. So first I will take copper 2 plus. We are talking about the electrons, right? I hope you remember I talk about the electrons. So our electrons is on copper ion, so it will definitely interference with our copper and also with nitrogen and OH minus. So here first our interference with copper 2 plus, we can use this equation. 2 n is 1. Now I am considering the copper 2 plus, so there is only one nuclei, so 1 I equals 3 over 2 plus 1. So when we are connecting with the other nuclei, you need to connect it with a multiplication, right? Because this is possibilities, right? Because this is possibilities, the ways of connecting each others. So we have to connect it with multiplication. So now I'm talking about the nitrogen atom, so just using that 2ni plus 1 rule. So here 2 n is 1, sorry, n is 1, yes, because only one nitrogen atom, and I is also 1 plus 1. And again when I'm moving into the OH minus ion, we have to connect it with multiplication. So here again I am using 2ni plus 1 rule. So 2 n is 1, only one nuclei we are connecting with, and here I equals 1 over 2 plus 1. Now the simplification, here from this one we got 2 to 4 over here we have 3, and here we have 2. So we would have 12 and 24. So we would expect 24 peaks for this specific problem for our spectrum, right, for our EPR spectrum. So this is basically the hyperfine effects. I hope you got some idea.